everybody, I'm going to talk a little bit about using amines in SM2 reactions. So there's kind of a reason that we have not talked about amines as nucleophiles a lot, especially in first semester when we learned about SM2 reactions and the different nucleophiles that you could use with those. So the reason for that is that amines and nitrogen tend to be a lot more nucleophilic than an oxygen or other types of nucleophiles that we tried out during the first semester. So there's a pretty big problem that you can run into in terms of over alkylation by doing like too many SN2 reactions in a row. So what essentially happens is if you've got an amine starting material, so I'm just using NH3, but you could have this happen with any type of amine as you'll see in a second. So I'm just going for the most extreme case of how far you can take this process. So we don't need, so it is already pretty much a strong nucleophile, so we don't need to deprotonate it or anything to make it really active. So all we're going to have is just the normal SN2 reaction here. Our X group is going to be, chlorine, bromine, iodine, tosylate, all those options. Again, we're going by the same SM2 type rules. So it's either a methyl or primary alkyl halide. Okay, so either a methyl with a halogen on it or primary, which is what I've got drawn out. So same SN2 type rules that we are always governed by. So we can do the first substitution, right? So this is our first SN2 reaction. We still have the 3 H's on there, and that nitrogen is now positive. That's not a big deal though, because we can just bring in NH3 as a base and deprotonate it, and then get to NH2. And that has also given me back my lone pair. So that's really the problem here, is that once we reform that and deprotonate it and reform the amine, so now we're at a primary amine. So the problem with this is that it's still a really good nucleophile. We still have a really available lone pair. The nitrogen's not as electronegative as oxygen, so it's more willing to share that lone pair. So if I just run into another equivalent of my alkyl halide, I can do the same reaction again. Okay, now I've done a double alkylation, and I can go do another acid-base reaction here to neutralize that amine out. And now I've got a secondary amine. But look what I did. I have the lone pair back. So it definitely starts getting a little bit harder as this gets bulkier, but it honestly doesn't slow it down that much. It's just going to go again. So another SN2 reaction here. We can do another acid base. Oops. Got our lone pair back, and we can do it again. That's what's so nightmarish about this process. Okay, once we're at this stage, so we have the tertiary amine here. Once we get to that final position where we've added now 4 alkylation products, once we get there, we're at the quaternary ammonium salt. And at this stage, I don't have any protons that I can deprotonate to get my lone pair back. So this is my final stopping point. And that's only because I can't get my lone pair back. It's just not possible. But it's not the most helpful thing if you don't want to have an ammonium salt. If you do want to have it, that's fine. So this whole process is very, very difficult to control. and stop at like a primary, secondary, or tertiary amine. Okay, there's really kind of one way that you can control it. So I will say it's fine if you want to make the ammonium salt. Okay, so like if this is what you're aiming for, it'll be fine. Like just go ahead and do it. If you want the primary, there's kind of two ways. One is more commonly used than the other one, but pretty much the only time that this is used is to make primary amines, so to stop right here. And pretty much the way that works is you use a very large excess of ammonia. Okay, so if you're just flooding this whole system with ammonia, and you have a huge excess of that over your alkyl halide, then you have less chance of over alkylation and you can more easily stop it at the first addition. The other very commonly used method to make a primary amine is using the Gabriel amine synthesis. Okay, so it's a really nice technique to get to the primary amine without having to do any weird excess or anything like that. Though in terms of atom economy, it's not awesome because you are throwing away a lot of atoms, and we will see that in just a second. So for example, if I have, they all are going to start with this phthalimide. Okay, and so I'm going to write that out. Oops. Okay, so that's phthalimide. The P is essentially silent, so don't worry about that. The pKa of this is about 10. Okay, so this is very similar to the 1,3-dicarbonyls that we just finished talking about for like the enolate reactions, except instead of a carbon in the middle, we've got a nitrogen in the middle. But the pK is very, very similar because we've got those two carbonyls that we can help delocalize the electron density into after we deprotonate this H. So all we need is just like some hydroxide base. And once we have that hydroxide, we can just deprotonate that phthalimide. Okay, once I'm here, it's a highly delocalized negative charge. So it's nice and stable, very good for just kind of chilling around. So if I add an alkyl halide to this, I'm essentially going to do just an alkylation like we did with our 1,3-dicarbonyls. Okay, so and again, this is SN2, governed by all the same SN2 rules that we've learned. And then I've done my alkylation, okay? And let's say we don't want all of this. If we just want the amine, we can absolutely get there. So think about this imide. Okay, this is our alkylated imide. So that imide is very similar to an amide, okay? So just like anhydrides, they're kind of similar to esters. This imide is going to be very similar to an amide, where if we just use, I'm going to go down here, basic hydrolysis conditions, okay, and we're specifically using basic in this case so that we get the amine and not the ammonium salt. So because if you use an acid, you will end up protonating your amine in the end, which could be okay, could be what you want. That's very common in a lot of cases. But we're just going to be essentially chopping off that amine that we've made, okay, our new primary amine. And then we're also getting this dicarboxylate. Space. Okay, so we're going to end up making that dicarboxylate as well. So this process, you can pretty much only make primary amines here. Okay, but you could always do this reaction and then do like reductive amination or something to get another amine. But it's a really kind of nice way of making it very specific to one addition and not over alkylating like you can if you're just using the amine itself. But the atom economy point comes into this part where all of this is essentially trash. So you're throwing away a really big chunk of material there in relation to like what we've added. So in terms of efficiency and atom economy, it's not the best, but it does get you the product that you want. So for that one, we're really looking for, we want to be really careful that we're not trying to do an SN2 reaction on anything that we are not allowed to do SN2 reactions on. So this follows all SN2 reactions. I'm going to say rules. Okay, so for instance, if we're looking at something like that primary amine, we would not be able to synthesize that because we can't do SN2 on a benzene, right? So we cannot do, we cannot make that. Okay, if we look at another example though, if we just brought in the benzyl bromide, sorry. If we want to make this, that's fine. So we can make that by breaking it down into benzyl bromide plus our phthalimide. Okay, whereas this other one, we would not be able to do an SN2 on an sp2 carbon. Okay, so make sure that we're following those same rules that we abide by for SN2 reactions, and we'll be all good. Alrighty, so hopefully this was helpful, and let me know if you have any questions, and we will keep talking about amines for a little bit.